This is the story of how we discovered one of the smallest and rarest objects in the night sky using the telescope with the largest field of view. The telescope in question is the Zwicky Transient Facility. Its purpose? To scan the sky and search for newly appearing light sources. On August 4th, 2022, it made an extraordinary discovery, a gravitationally lensed supernova, hereafter named Supernova Zwicky. From the full ZTF field of view, let's zoom in on the quadrant containing Supernova Zwicky. To take a closer look, we transition to an image captured by the Very Large Telescope in Chile. Finally, we zoom in even further with observations from the powerful Keck telescope on Mauna Kea in Hawaii. And what do we find? 4 dots corresponding to 4 magnified images of Supernova Zwicky. Supernovae are exploding stars that we observe routinely in the universe, but Supernova Zwicky is a very peculiar case. The 4 dots of Supernova Zwicky are created by a remarkable phenomenon called gravitational lensing. When we observe a distant object, such as a supernova explosion, a galaxy can be positioned between us and the supernova and act as a gravitational lens. Massive galaxies are able to bend and magnify light rays from the supernova, causing the light to travel in multiple paths around the lens galaxy. As a result, we can see multiple images of the same event. That's precisely what happened with Supernova Zwicky. Instead of witnessing the supernova explosion once, we observed it 4 times. Supernova Zwicky belongs to a special class of supernovae called Type 1a supernovae. These stellar explosions always occur in a similar way, giving them a similar brightness. Type 1a supernovae are an important tool for measuring cosmic distances. The fainter they appear, the further away they must be. That's why we call them standard candles. But Supernova Zwicky didn't look like other Type 1a supernovae. It was much brighter and further away. Let's sketch a picture of how far away Supernova Zwicky is from us. The Zwicky Transient Facility, or ZTF, can usually discover Type 1a supernovae up to distances of around 1.3 billion light-years, which astronomers refer to as a redshift of 0.1. ZTF has found thousands of such objects, but it had never seen a Type 1a supernova so far away as Supernova Zwicky. Gravitational lensing made this incredible discovery possible. The lens galaxy acted as a cosmic magnifying glass and made Supernova Zwicky 25 times as bright. That's how we can observe it at a distance of almost 4 billion light-years, or a redshift of 0.35. While ZTF allowed us to discover Supernova Zwicky because of its anomalous brightness, it was not powerful enough to resolve the 4 separate images. Supernova Zwicky just appeared as a dot. We then turned to larger observatories, such as the Very Large Telescope in Chile, to learn more about the supernova. And it was only when we observed Supernova Zwicky with the Keck telescope in Hawaii, equipped with adaptive optics technology, that we could see the 4 separate images. Adaptive optics corrects atmospheric distortions using a laser, providing us with an exceptionally sharp view from Earth. Supernova Zwicky was also observed from space with the Hubble Space Telescope. And observations of Zwicky's afterglow, the nebular phase, are scheduled with the newly launched JWST. So what did we learn about Supernova Zwicky through all these observations? The images formed by gravitational lensing generally don't all appear at the same time, because the light rays travel along different paths. For Supernova Zwicky, however, we saw that the 4 images appeared almost simultaneously. Even though the light from all of them traveled 4 billion years in different trajectories around the lens galaxy, the difference in arrival time at Earth was less than a day. We also learned that the Supernova Zwicky system is extremely compact. With image separations of around 0.15 arc seconds, or 10 to the minus 5 degrees, it's one of the smallest lens systems ever found. Seeing Supernova Zwicky from Earth is comparable to reading a newspaper from a distance of 10 kilometers away. We measured the stellar mass of the lens galaxy to be around 12 billion solar masses, quite light for a galaxy that acts as a gravitational lens. Furthermore, our lens models indicate that the brightest images, A and C, should have actually been the faintest, suggesting the presence of additional lensing effects from stars, substructures, or dark matter in the lens galaxy. Compared to other known lens galaxies, the galaxy that lensed Supernova Zwicky turns out to be a special one. It's much smaller and lighter than any lens galaxies we've encountered so far. This diagram shows the masses and angular sizes of known lens galaxies, and it shows that Supernova Zwicky is an outlier. There's one other known supernova lensed by a single galaxy, 16 GeU. And when we add 16 GeU to the diagram, we see that these lensed standard candles allow us to uncover a new population of light and small lens galaxies. So what's next? With the advance of the next generation of telescopes, like the Vera Rubin Observatory in Chile and the Nancy Grace Roman Space Telescope, we anticipate discovering hundreds more of these rare gravitationally lensed supernovae. These will provide us with insights into the expansion rate of the universe, the distribution of dark matter in lens galaxies, and the nature of distant supernova explosions. Bright times lay ahead!